The difference here is the following. Let me rewrite this part for you guys so that way you will be unable to see. Oh, yeah, it is here actually. It's over there. Let me show you, it's over here. So this is our Hamiltonian. This is our Hamiltonian. It has a potential from atom number A, potential from atom number B. So we have these two potentials which is all related to each other. So in other words, we have three terms, one is this one and this one. Now what we did was, we put the T and the V together, VA together. So this becomes H naught. And then we put this VB as our HI. So that's what we did. In other words, we split in this particular format. And now I'm going to show you why we do this. In other words, why we do what we're doing here. So here is a reason. So the reason is on this board, and I'm going to show you here. And this part is quite important. The important thing is the calculation. Once we split them together, so here is a key idea which shows up over here. So here's the key idea. So the key idea is to have H naught being the same as our hydrogen atom. The key idea is have H naught being the same Hamiltonian, as our hydrogen atom. So this is the key idea. You know, when we separate them, we do not separate them arbitrarily. So this term here is exactly the same as hydrogen atom. You remember, here's the T kinetic energy plus the potential. So this part is a Hamiltonian in this case. Does it make sense to you? Because you have a kinetic energy, same thing. In fact, if you wish, we can write this guy, H0. We can write this H0 right in HA. They are exactly the same thing. So this is on the atom number A. H0, HA are exactly the same. There is no difference. And you could also, in fact, write TVB as your HB. They are exactly the same. You can write T plus VB as HB. They are both okay. It doesn't matter. The reason why this guy doesn't matter is because, or let me write down the equation. You can also write in the following format. There's no problem. The reason why it does this is the following. Let me show you the Laplacian this itself. You remember Laplacian has partial x square term like this, and you have a y and a z exactly the same way. Did you see here we have an r prime here? Did you see r prime here? Here are, but here's r here. Now if you change from the x to x prime, the expression are exactly the same. The expression are exactly, there is no difference. The main reason was these two are completely just a variable in this sense. And let me show you why these are exactly the same. So you see there, x differs by x prime by a fixed constant. Let's call it r, x direction. There's no need to call them. So in other words, I'm explaining why these two are exactly the same. The reason was the x and x prime is just differs by the position. Here's from here to there. That's a position vector. Assuming this is your 0, but now for this one will be the r, right? This will be differs by r. Does it make sense to you? You know, x prime just differs by a constant vector. It's just a constant vector. Now, if you take partial over partial x, and this must be equal to each other. Because this guy is a constant. Whenever you take partial, same. Second order derivative, same. So therefore, these two are exactly the same. In the sense that this t can be a TA or can be TB. They are exactly the same. If we use as a TA, and this will be TA. If a TB, this will TB. So either will be fine. So therefore, we can write a TA just equals TB. TA just equals TB. And in our case, we choose this one as our TA, so this will be HA like this. I can also choose them to the B. So there's no question on that either. So I can choose either TA or TB. And they give me exactly the same results, either TA or TB, and these two will be no difference whatsoever. Okay, so just remember, how do we separate these matters? That is our eigenenergy, we separate them. Now, once we're done with this, now step number 3 comes, which is the continuation that we did last time. Then what we do the following. We're going to form the matrix like this one here, exactly the same one as we did last time. So we form a matrix for H hat like this. So we just form a matrix like that. So the matrix element will be following. I'm going to denote A hat B like this. So the direct notation A is just to mean this guy's here. Could you guys write this down? Just to simplify my notation, my A here, these two A's are exactly the same, and now my B is like that. Okay. Are we good so far? And that is what we are doing. And we also have the matrix elements AA, and of course BB, and of course we also have a BA. So like these ones. So that is why I said now the formula matrix. So the matrix elements will be 2 by 2 matrix elements. Will be this term, and this term, and then we also have a VB. This VB is the potential, which I show you quickly. So this VB itself is just this vector VB. VB hat is just the native E squared 4 pi epsilon 0 r prime like this. So that's a VB. My H hat is just VB. This you see here. H hat is VB. So I can plug it in, do the calculation. In our case, when we do the calculation, so this is the Hamiltonian matrix comes out. So we have 2 by 2 matrix. And we will assume A, H hat, I, B, this equals negative T. And this also equals a negative T. So this is the off-diagonal element. So I have off-diagonal elements, negative T, negative T. I will explain why it is negative. All right, it's not obvious why it must be the negative. And I will explain this shortly for you guys. And you will see we will use the negative T there. And of course, we also have the diagonal term, and I will use delta like this. So in other words, this term here, there will be the delta. So I use a parenthesis referring to this term equals negative delta. This term equals negative t, and that's negative delta. And that's a 2 by 2 matrix. Are we good so far? So that is the so-called matrix representation of our. I want to show you the where is my direct notation. So this is direct notation which we use here. That's direct notation. And then we use this way over there, so that's we form the matrix element. And when you solve for this eigen value problem, and then you should be able to get the results on this side. So I'm going to show you on this side the results. So now this is the entire calculation. Okay, my eraser will be better. Yeah, if you guys have questions, just stop me. So in this case, now we are ready to show you the results. Water. And this part is essentially just show you the entire results, and I hope this will be easily solvable. Here. I need to wait for it, because otherwise it will not easy to write on top. Let me try it. So now, when you diagonalize this matrix, you get two values. You get an E1, and the first order, put the 1 on top. That's first order. And 1 will be lower, which we'll call it e to the negative t delta. And I need to wait a few seconds. Right over here. E1 t equals negative delta. 1 is a negative t, like this. The other one will be E2 first order plus t, like this. So essentially, we have two roots involved when you solve for this. And the wave function also can be calculated immediately. So in this particular format, I hope this is good. So my wave function psi 1, this is first order, this is the first wave function with the square root 1, 1. So this is my first wave function. The second wave function is 2, 1, square root 2, 1 minus 1, like this. These will be two wave functions which we have. And now we are end of it. In other words, we found everything that we needed, so in order to get the results in this case. So this is our the equation in order to, these are our wave functions. Now, let me show you the how this actually works. So, I think I will wait on this. Let me use this board. That board becomes a little bit messy. It's not that easy to, I didn't realize it's pretty dry. So I'm going to roll over here. So the following answer for our problem will be here. So the wave function, those two wave functions will be written. That is in terms of the, so this is just a metric element. We need to put the wave function over here. That's psi 1, 1. So we have a normalization 1 over square root of 2. Now watch carefully. This time we will put the basis function into it. Here is a matrix elements representation. But now down over here, we're going to represent in terms of the original basis function. That will be phi A 1s plus phi B 1s wave function. And this is our first wave function. Did you guys see the dimensions? There we use a 1, 1. The 1 is the real means phi A 1s. Another one is phi B 1s. So the first row referring to the first atom. Second row is the second atom. Did you see that? And this is quite important. This particular feature called the linear combination of atomic orbitals. So this is called a linear combination of atomic orbitals. So what it does is essentially tells you originally these are the atoms, atom wave functions. But now the molecule becomes a linear combination of the atomic molecules. And this is usually called LCAO. In the literature, they call it LCAO, which is linear combination of atomic orbitals. Let's sketch this orbital in the space. We're going to sketch this orbital in the space. Here's atom A, here's atom B. Yeah, make sure you do write this down in your notebook, which is quite important. So did you see we have a plus sign here? So therefore, these two wave functions, when you draw them, do something like this. You have a maximum at an atom location, another maximum at an atom location, and something like this comes out. And I did not draw very well. I should draw a little better. So, jumps down like this. And that's the wave function. And these are states. Did you see you have a non-zero value here? Here you have a non-zero value. And this part has a non-zero value there. And these states called a bond state. Bonding state. They form the bonds. So in other words, because they share some kind of electrons in between these two atoms, so this is called a bonding state. And they form bonds. That's why the entire chemistry is quantum mechanical. Entire chemistry is quantum mechanical. You have when you form the bonds, that becomes a molecule. So this is become the molecules in this case. So this is what we have. Any question on this part? Any question? So in between them, you have like now. This is to be more precise. We should use the charge density to represent. Charge density is just L squared like this. It's called charge density. It's the positive. And this is usually called a bonding orbitals or bonding state. In chemistry, will be bonding orbitals, molecule bonded. Now we have another state, which is over here. Did you see have a negative sign there? Another state, we have a psi 2, 1. And we have phi A minus phi B like this. We have a negative sign. In this case, this density is look like this now. Of course, it should be negative, but not negative like this. It's better to use the wave function. Let me plot the wave function because that all thing would so like this. It has a feature. So this is called an antibonding orbitals. So when you see you close with this, you get a negative sign, and over there. So you see this is called an antibonding orbital. Antibonding state. for physics, orbital for chemistry. In chemistry, this is called antibonding orbitals, and in physics, we just call it antibonding state. So they are the same thing. If we plot the density, then the density will look like this. These antibody orbitals, it's very easy to dissociate. So this is due to chemical could be dissociated. They are very useful for the chemical reaction. And this chemical reaction, which means you can rip these two hydrogen atoms apart. When you rip them apart, you can have a chemical reaction. It's essentially you already in H2 plus, but now it becomes H2H in this case. And it was debating, if you rip this particular electrons apart, these two atoms apart, this is something very interesting when. Folks, take a look at this. Here's H1, and we have a negative electron situated over here. Now, Alex, if you separate these two atoms, and you were wondering where this electron is going to be eventually will be, right? If you have one single hydrogen atom, you're perfectly fine. But what happens if you make them separate these larger and larger and larger and larger like this? So you know where this electron is going to be, right? That makes sense to all of you? You know, in the beginning, you have in between. If you rip them really, really far apart, where this will be? This is a very difficult question to answer, right? Because you don't know where that is. It turns out, quantum mechanically, if you did not measure precisely, they will appear in these two hydrogen atoms simultaneously. This is a very weird instance that you rip them apart, but this electron still hovering like that. So in other words, when you rip them apart, electrons still hovering like that. However, if you put the hands across this, then there is no communication with these two atoms, then electron will jump to one particular atom. If there is no separation, this means you watch some videos, you will say, that's observable or something. Well, that means you have external interference going on. If you have truncated that in that case, then, well, the wave function will be disrupted by your barriers. You set up the barrier. Then this electron will jump to one particular atom. Depends how accurate you separate them. So that is the probability case. And this is a very difficult and not easy to understand because eventually they were going to go over that particular direction. Okay. Any question on this problem? So this is how do we solve this completely? We set up the matrix, diagonal matrix, and it gave us this results. And now we have not discussed the eigenenergy completely. So here's eigenenergy spectrum. In the beginning, we have two 1s level. They both are the 1s level. There's no difference. But when it goes to each other, this energy level, one is moved upward, one is moved downward. Make sure you guys take notes on this. If next week we quiz you on this, you make sure you are able to understand. So this energy level will be split. One will be lower, which is down here, and one will be higher, which is over here. And this orbital down here energy, this is called a bonding state. And this is antibonding state. So this is antibonding. One is a bonding state, one is antibonding state. So antibonding state where energy will be higher, bonding will be lower. Especially the bonding state will be close to each other. Antibonding state will be away from each other. That's called antibonding state. And one thing that I did not explain, did you see I have a negative T here? So here's the negative T reason. And we'll ask you about this on Monday. Why we get a negative sign here? This negative sign is coming from the potential self. Did you see we have a negative sign here? So you see a negative sign here. So if you do the intervals phi a, and that's e to the negative 4 pi f0 r prime phi b dr, like this. If we do the interval, this guy will produce a negative sign. That's why this will become negative. And this interval is also called hopping interval, because it hops from one atom to another atom. So this is called hopping interval. The delta is just energy, rigid energy shift. There's no significance in the sense that when we put together, this energy level actually physically shifted upward, but there's not a lot of physical significance in this case. So that's that. Now once we're done with this, I hope I have enough time. And now we're going to move on to one of the very important example. When I prepared the class, I was struggling with, perhaps, it's here. What's going on here? All right. Well, I did not fix this one. So, in this case, we're going to talk about something called a Stokes effect. I was hoping that we have enough time to Stokes effect, and then before we move on to the variational principle. Do you guys still remember Zeeman effect? Tobin, what's the Zeeman effect?
It's applying a magnetic field onto a light spectrum and watching the bend.
Then and the beam starts to split, right? Well, in this case. The Stokes effect, Zeeman effect, they are brothers, essentially. They are brothers. One is British, one is Dutch, so that's essentially. But what the Stokes effect does is that here you use an electrical field, and here you use the magnetic field. It's very easy to learn these together. The interaction Hamiltonian for the Stokes effect is the following. Just dipole moment operator times electrical field E. Folks, this is the electric field. Okay, so that's E, the electric field, which we have. And for the Zeeman effect, folks, we are a chapter away from us for the moment, but this is very close now. So the Zeeman effect, we use the magnetic moment. This is the dipole moment. This is called magnetic moment times the magnetic field. Be like this. They're one-to-one correspondence. And so our D is just charge times the position vector. And the Zeeman effect, it turns out, is very much similar. Stokes effect very much similar to the Zeeman effect. So it's exactly the same. Here you have one spectral line, like this, and you split into three. Here you want one spectral line and one in the middle, like this. You also split into three. So that's exactly the same when you apply that. So without electric field, it's a single line. With electric field, you have three lines. Same thing over here. Of course, the Zeeman is more complicated because you have orbital momentum. Here we don't have orbital momentum, so to speak. So that's why this is the harder for the next chapter, and this will be a little bit easier. How do we do that? Now let me show you what this actually means. Well, in a hydrogen atom, we have one s orbital here, and we have 2s, 2p orbital over here. So remember, we have 1s and 2s, 2p orbital over like that. If we have the no electric field, you have transition back down, and you will see one line like this. But when you apply electric field, this particular level will split. It will split like this. One will go a little bit up, one will go a little bit down, and the other one will be in the middle. It will split in this format as well. So then we have a transition. Now the 1s orbital does not split. Just p orbital itself will split in this case. Then you have a one line here, another line here, another line like this. So now you see you have three lines comes out in this way. So just remember, and that is how do we get the Stokes effect. So essentially, we're jumping from here to there, you get one single line, but you have three of them, so it will split this way. And I will show you the key steps also, and then we're going to read the books this time. Folks, could you take out a book, please? And this will be the example number 2. We're going to read the book. Yeah, everybody read the book, please. And we're going to read the book this time. So this in the book is 147, section 5.4.2. 5.4.2. So 5.4.2. This section. And we are going to ask, you ready for that? So I will ask Tobin, could you read the first paragraph under 5.4.2?
The Stark effect refers to the spectral length splitting under external electric field. Hydrogen's n equals 2 state is fourfold degenerate, 2s, 2px, 2py, and 2pz. When it is placed in a uniform electric field F along the z-axis, the state splits. A, compute the split eigenenergies, and B, compute its wave functions in terms of unperturbated eigenstates.
Thank you. Cody, please. Next paragraph, please.
First, you define the interaction Hamiltonian, H sub I from E and M. We know this is a dipole interaction, H sub I equals negative D dot F equals plus E R hat dot F equals ER at cosine theta, with theta being the angle between the dipole moment and electric field. Because we have a fourfold degenerate state, we need to form a 4x4 matrix for H sub I. Direct notation of phi sub I, H sub I, and phi sub j, where phi sub I are 2s orbitals equals r20, y00, and 2px equals r21, y1 plus 1, 2py. R21, Y1 minus 1, 2PC equals R21, Y1, 0. Since the spatial part, R of R, is the angular part, YLM theta phi are separated, the integration, direct notation, phi sub I, H sub I, phi sub j, can be carried out separately because the radial integration of R is almost always non-zero, and the angular part may be 0. Carry out this integration first, for instance, that.
Okay, thank you so much. Aisha, could you read the expression 5.4.7?
Direct notation 2s, H sub I hat 2px equals triple integral R sub 2, 0, y sub 0, 0, ERF cosine theta, R sub 2, 1, y of 1, 1, r squared sine theta, whose angular part is the double integral of y sub 0, 0, cosine theta, y sub 1, 1, sine theta, d theta, d phi, equals the double integral of y sub 0, 0, cosine theta, y sub 1, 1, d omega.
Great, thank you. Do you guys remember that the 2s is R20, Y00? Any question on that? If you remember, that is how we write that notation. Psi, N, L, M, this written Y, R, Y, M, like this. So that's the notation we use. For instance, if the 1s orbital with 1, 0, 0, so that's what 1, 0, here's 0, 0. If 2s orbital with 2, 0, 0, 2, 0, and this will be the 2, 0, 0 over here. So that's how we. You guys good? Can I get a thumb up? Everybody give me a thumb up. Okay, so that's very important. All right. So And next one, I would like to ask the Alex to read.
5.4.9.
Yes, read it, exactly, yeah.
Cosine theta times y sub lm equals the square root of l plus 1 squared minus m squared over open quantity 2l plus 1 closed quantity open quantity 2l plus 3 closed quantity times y sub l plus 1 m plus square root of l squared minus m squared over open quantity 2l minus 1 closed quantity open quantity 2l plus 1 closed quantity y sub l minus 1.
Yeah, go on, please.
This shows that cosine theta y sub lm is represented by two other spherical harmonics. Therefore, cosine theta y sub 1, 1 only yields y sub 2, 1 and y sub 0, 1 because all the spherical harmonics must be orthonormalized. The double integral d omega complex conjugate of y sub lm y sub L1 M1 and y sub L2 M2 equals double integral theta from 0 to pi of phi from 0 to 2 pi of sine of theta d pi complex conjugate of y sub L1 M1 times y sub L2 M2 equals delta L1 L2 times delta M1 M2.
Keep on going, please.
Where d omega sine theta d theta d phi equals the solid angle finite element.
Okay, stop here. Any question on these intervals themselves? These are just identity matrices. Essentially, when you do in YLM, it's always integral like this. And the question that before equation 5.4.9, and essentially you can do the interval directly, but it's a whole lot easier to use the iteration relation 5.4.9. So that's the key. When we write this part, we want that original with them. If you do the interval itself, it's not generic, but the bottom one is much more generic. In other words, if I have a test, and you will be much easier to work with. Cody, could you read the next paragraph? I'll start with the then.
Then we have double integral of complex y sub 0, 0, cosine theta y sub 1, 1, d omega equals 0. Therefore, the only non-zero element is direct definition 2s, h sub I, 2p z. Direct definition 2s, h sub I, 2p sub z equals integral from 0 to infinity of e fr sub 2, 0 of r to r sub 2, 1 of r squared dr times integral of phi from 0 to 2 pi and mu of theta from 0 to pi of y sub 0, 0 of theta phi cosine theta y sub 1, 0 d omega. The angular integral is integral from 0 to pi, and the other from 0 to pi, y sub 0, 0, open quantity, the square root of 1 plus 1 squared minus 0 squared all over 2 plus open quantity, 2 plus 1 plus 1 open quantity, 2 plus 3 plus quantity, times y sub 2, 0 plus square root of 1 squared minus 0 squared all over 3 times y sub 0, 0 close quantity, d omega equals 1 over root 3. The radial integral is the integral from 0 to infinity of r sub 2, 0 of r, lowercase r, capital R sub 2, 0 of r squared dr equals negative 9 a naught over root 3.
Thank you so much. And Toby, could you read the next two paragraphs, please?
Finally, direct notation 2s h sub I hat 2z equals EF 1 over root 3 times negative 9 A naught over root 3, which equals negative 3E A naught. Our final matrix H sub I is first row 0, negative 3E F A naught, 0, 0. Second row, negative 3E F A naught, 0, 0, 0, and then the last two rows all being zeros. Diagonalizing it produces 4 roots. E to the first order equals plus or minus 3E F A naught, 0, 0. The eigenenergies of H hat equal H hat naught plus H hat sub I. So the first order are E to the 0th order plus 3E F A naught, E to the 0th order minus 3E F A naught, and E to the 0th order and E to the 0th order, where E to the 0th order is the external field free to S2P energy. The two roots, i.e. E naught, are double degenerate. B, the wave function for the two SP hybridized levels with E1 equals E to the 0th order minus 3E F A naught, and E2 equals E to the 0th order plus 3E F A naught, are psi sub 1 equal 1 over root 2 open quantity K of 2S plus K of 2PZ closed quantity, and psi sub 2 equals 1 over the square root of 2 open quantity K of 2S minus K of 2P sub Z closed quantity. In the absence of an external electric field, the transition from the 2P state to 1S state emits a photon with energy delta E equals E to the 0th order minus E sub 1S. With the external field, if the electron is initially in the psi sub 1 state, its transition to the K1S state emits a photon with energy delta E equals E sub 1 minus E sub 1S, which equals E to the 0th order minus E sub 1S minus 3E F A naught, which is 3E F A naught less than delta E. But if the electron initially is in psi sub 2, then the photon energy is 3E F A naught higher than delta E. The two states, psi sub 3 and psi sub 4, that do not have energy change produce a single line. This means that spectrally one single line is split into 3 lines. See figure 5.2 to start with that.
All right, thank you so much. Did you guys understand the entire things? When you read together, you feel this is quite important. It's really systematic. It shows two of them still degenerate, and then there is a coupling between the S2S state and PZ states, and this will be actually in the selection rule, which we will do that. So this is the one thing that I struggle on this, and I was wondering whether I should present this because it's a little bit lengthy to read them also. But do you guys enjoy this part? This is a really one-to-one correspondence that I just mentioned. Okay, now I want to squeeze in one more thing because I hesitate to not present this, guys, for you. This was my section 5. And this one will be very quick because we need some time left for the spin chapter for the electron springs. So this I usually do not teach because its variational principle is a little bit more challenge in a way that than the rest of the materials. But I found a good way to present such that we do not need enormous amount of things involved. Let me first show you the key idea. The key idea, this is different from the perturbation theory. Perturbation theory just make corrections, order higher, and make better. And it's different. The key idea is we find or many more variational parameter, maybe 1 or 2, but let's just call the lambda like this. We don't know what this lambda is, but we will assume there is a lambda involved. So the total energy will be a function of lambda. So that's the job. And you may wonder, how do you figure this out? Well, it's based on experience. If you have no experience, sorry, you cannot do this. But if you have more experience, you could do this. And there will be a lot more to gain from doing like this. Let me quickly show you an example what that means. Suppose my s orbital, you remember, let me write a little better on this orbital. And so the s orbital we already wrote over there. So 1 over 2a cubed, like this. And so e to the, now on the top, I normally have r divided by a, right? That is what we have. I think that is, I hope I did not miswrite anything. Yeah, oh, this is the pi, not 2 pi. A like this. Yeah, exactly. So this is a naught. This is Bohr radius. So this is the wave function we used this before. This ground state for when s orbital, 1 over square root pi a cubed, and e to the negative r a naught, like this. So that's what we did. So far, there is no parameter that I ever used. Now watch carefully. Did you see I have a here? I put a lambda in it. Did you see I have a good here? I put I change this one to this lambda on the top, this lambda will be on the bottom, like this. So essentially what I did was I forcefully plugged this lambda into it. When the lambda equals 1, Alex, this will go back to what I had before. No problem. But if the lambda not equals 1, we can optimize it. So therefore, the key idea was that I can optimize such a way. This is the old Hamiltonian, original Hamiltonian. I do not separate them, not to be separated. The edge self is a Hamiltonian original. We do not separate. In the perturbation theory, we separate. But here, variational principle, we do not separate them. And then here we have another 1s orbital put inside of this. And this is my eigenenergy, lambda. Are we good so far? So then we do the interval like this. So essentially, we purposely plug in this particular called variational parameter, which put over there, and that must be dependent on lambda. Now see what's the magic. Magic is this. Take partial lambda of e of lambda divided by the lambda. Folks, take a look at this. Put them equal 0. So we get a variational principle. This will give us either minimum or maximum. This could be either minimum or maximum, or maximum. Let me ask Cody, when that will be the maximum? When we will get a maximum? In other words, I said when e equals 0, you get a solution, either get a minimum or get a maximum. Under what condition we will get a maximum? Anybody help?
When the double derivative is negative.
Exactly. Did you hear it? Did you hear it? Did you hear it? When the double derivative is, how do you remember so good? Good job. Yeah, you remember when the double, okay. Alex, you make my day. So this is how you determine it. If this guy is a larger than 0, you get a what?
You get a minimum.
You get a minimum, exactly. Otherwise, you get a maximum. So that's what you get. And that is the key. That is the key. That's the key. And this entire spread is just based on this idea. And I hope it did not overwhelm you guys. This is just a simple way to present this. Extremely simple, just about 5 minutes. And that way. Entire calculation is just based on this simple idea. the trouble was that I run out of time, but I will go back and I will use probably about 30 minutes maximum, and then we will go to the spring, the chapter on the electron springs. Okay, that is my focus. But this part I cannot hold because I have a very nice portion of the H2 plus molecules can accurately present this, guys. Okay, very good. Folks, we're going to end this now. Make sure you do turn in the homework. And next Wednesday,